In 2017, astronomers detected something extraordinary. An interstellar object later named Oumuamua had entered our solar system. It was fast, it was strange, and it defied expectations. 2 years later, a second interstellar object, comet 2I Borisov, confirmed that Oumuamua wasn't a fluke. Now, in 2025, it has happened again. A new object has appeared on the radar, and this one is called 3I Atlas. Unlike Oumuamua, which we noticed 5 days after it flew past Earth, this time we're ready. Spotted on July 1, 2025, and listed by the International Astronomical Union's Minor Planet Center, 3I Atlas raised eyebrows in the astronomical community. It first showed up in the Near-Earth Object Confirmation Page flag for follow-up. But this wasn't just another rock on a long elliptical orbit. The moment astronomers began fitting a trajectory, the signs were clear. This object isn't from around here. Prepare yourselves. We begin. On July 1st, 2025, astronomer Larry Deneau clicked submit on what looked like another ordinary rock floating through space. The object appeared as a faint dot against the star fields, magnitude 18.8, over 2 million times dimmer than the North Star. But this dot was moving. Not the lazy drift of a typical asteroid, but something urgent, purposeful. The preliminary calculations made Deneau pause. The object's speed suggested it wasn't gravitationally bound to our sun. Think of it like a baseball thrown so hard it escapes Earth's gravity entirely, never to return. Atlas operates as part of a global network designed to protect Earth from cosmic threats. Every night, its powerful cameras capture images of the same patches of sky, comparing new photos with previous ones to spot anything that has moved. Most detections turn out to be main belt asteroids following predictable orbits, or near-Earth objects on well-understood paths that pose no immediate danger. The system processes thousands of observations each night, flagging objects for human review based on their motion and brightness. When Deneau reviewed the latest batch, this particular object stood out not because it was bright or large, but because its motion didn't fit the expected patterns. Within hours, observatories across the globe were turning their instruments toward this mysterious visitor. The Minor Planet Center flagged it as a near-Earth object, initially catalogued as A11PI3Z. The designation looked routine, but the numbers told a different story. The first follow-up observations came from telescopes in Arizona, where the Catalina Sky Survey team quickly confirmed the object's unusual trajectory. David Rankin captured clear images, showing the visitor as a distinct point of light moving against the background stars. His photographs would become some of the first documented evidence of this cosmic wanderer. As more observations poured in from facilities around the world, the picture became clearer and more extraordinary. This object was traveling at 66 kilometers per second relative to our Sun, far exceeding the 42 kilometers per second needed to escape our solar system forever. It was moving faster than any known asteroid or comet should move if it belonged here. The European Space Agency's Planetary Defense Team immediately took notice. Their telescopes in Spain and Chile began tracking the object, adding crucial data points to determine its precise trajectory. Each new observation refined the calculations and strengthened the case for something truly remarkable. The astronomical community buzzed with excitement. Could this be another interstellar visitor, like the mysterious Oumuamua that had captivated the world in 2017? The trajectory calculations suggested something even more extraordinary. This wasn't just another interstellar object. It was moving faster and following a more extreme path than any visitor astronomers had ever detected. Professional astronomers began requesting emergency telescope time, knowing they might be witnessing a once-in-a-generation discovery. Amateur observers started sharing the coordinates on social media, mobilizing a global network of sky watchers to help track this cosmic messenger. Next, we dive deeper into the moment astronomers realized they were witnessing something unprecedented. The breakthrough came when citizen scientist Sam Dean started digging through archived telescope data. Working late into the night from his home computer, Dean began systematically searching through weeks of Atlas observations, looking for earlier glimpses of the mysterious object that had just captured the world's attention. His persistence paid off in spectacular fashion. Deep in the archives, Dean discovered clear images of A11P I3Z dating back to June 25th. These weren't random lucky shots, but a systematic trail of observations that had been sitting unnoticed in the data for over a week. Each image showed the object progressing along its path, a cosmic breadcrumb trail waiting to be discovered. These pre-discovery observations transformed everything astronomers thought they knew about the visitor. With 6 full days of tracking data, instead of just hours, the orbital mechanics calculations became dramatically more precise. The margin of error shrank from wild estimates to mathematical certainty. With the extended dataset, astronomer Ye Quanji located even earlier observations from the Zwicky Transient Facility dating back to June 14th. The trail now stretched across nearly 3 weeks, providing an unprecedented baseline for calculating the object's true trajectory through space. The refined calculations revealed numbers that made seasoned astronomers pause in disbelief. The object's eccentricity measured 10.4, plus or minus just 1.1. In astronomical terms, this number represents something almost beyond comprehension. Our Earth follows an orbit with an eccentricity near 0, meaning we travel in an almost perfect circle around the Sun. Even the most elongated comets in our solar system rarely exceed an eccentricity of 3. An eccentricity above 1 means the object follows a hyperbolic path, entering our solar system once and never returning. But 10.4 represents something extraordinary. The highest eccentricity ever recorded for any object passing through our cosmic neighborhood. Think of it like a stone skipping across a pond. Except this stone is moving so fast it barely touches the water before launching into the air forever. The mathematics told an unambiguous story. The object was following what astronomers call an unbound trajectory, confirming beyond any reasonable doubt that it originated from interstellar space. This wasn't a long-period comet returning from the Oort cloud, or an asteroid knocked out of the main belt. This was genuinely alien to our solar system. Professional observatories around the world immediately recognized the significance. The International Astronomical Union moved with unusual speed to officially designate the visitor as 3-1 Atlas, making it only the 3rd confirmed interstellar object in recorded history. The Roman numeral 3 marked its place in this exclusive club of cosmic wanderers, while Atlas honored the survey telescope that first spotted it. The designation carried profound implications. Astronomers now had mathematical proof that objects from other star systems regularly pass through our cosmic neighborhood, invisible messengers carrying information about distant worlds and alien planetary systems. But this visitor held even more surprises, starting with its unprecedented speed through our solar system. 3I Atlas is not just fast, it is moving at velocities that fundamentally redefine our understanding of interstellar travelers. At 66 kilometers per second relative to our Sun, it outpaces both previous interstellar visitors by significant margins. To put this incredible speed in perspective, you could travel from New York to Los Angeles in less than 2 minutes, or circle the entire Earth in under 11 minutes. This extreme velocity tells a story of violent cosmic events that occurred millions of years ago in a distant star system. Objects don't achieve such tremendous speeds through gentle gravitational nudges or slow orbital decay. Something incredibly powerful ejected this visitor from its home system, launching it on an epic million-year journey through the cold darkness of interstellar space. The physics behind such extraordinary speeds involves catastrophic gravitational encounters with massive objects, close stellar passes, or even the violent death throes of stars themselves. When a massive star undergoes a supernova explosion, the tremendous energy release can fling nearby objects at incredible velocities, essentially turning them into cosmic bullets racing through the galaxy at unimaginable speeds. Current astrophysical models suggest 3I Atlas has been traveling through the vast emptiness of interstellar space for millions of years, possibly since before complex life evolved on Earth. During this enormous span of time, it has experienced the deep cold of the cosmic void, with temperatures approaching absolute zero, while radiation from distant stars slowly altered its surface chemistry and structure. The object's incoming trajectory strongly suggests it originated from somewhere within the galactic disk, the flat plane where most stars in our Milky Way galaxy reside. This directional information provides tantalizing hints about a stellar encounter that occurred long before human civilization began, when our entire solar system occupied a completely different position relative to neighboring star systems. What makes this record-breaking speed even more remarkable is that 3I Atlas shows no signs of slowing down as it approaches our Sun. Unlike objects born within our solar system, which follow predictable elliptical orbits governed by solar gravity, this interstellar visitor will maintain its tremendous velocity throughout its entire passage. It will swing past the Sun like a cosmic slingshot, gaining even more speed before racing off into the darkness beyond Neptune. The gravitational influence of our Sun will bend the visitor's path slightly, but cannot capture it into a permanent orbit. 3I Atlas carries far too much kinetic energy to be trapped by solar gravity. After its brief encounter with our star, it will continue its eternal journey through the galaxy, carrying with it whatever secrets it holds about its mysterious place of origin. This incredible speed also creates urgent challenges for astronomers hoping to study this rare visitor from another world. The number 6.3 will forever define 3I Atlas in the annals of astronomical history. This orbital eccentricity represents the most extreme trajectory ever documented by human science, completely dwarfing even the remarkable eccentricities of previous interstellar visitors like Oumuamua's 1.2 and Borisov's 3.4. Understanding orbital eccentricity requires thinking carefully about the fundamental shapes that objects can follow through space. A perfect circle has an eccentricity of exactly 0, representing the most stable possible orbit. Earth's slightly oval orbit around the Sun measures just 0.017, so close to circular that our planet experiences only minimal variation in its distance from the Sun throughout the year. Most objects in our solar system follow similarly predictable patterns. Even highly elongated orbits like that of Halley's comet, which stretches far beyond Neptune before returning every 76 years, reaches an eccentricity of only 0.967. These are bound orbits, mathematical curves that close upon themselves and repeat indefinitely. When eccentricity exceeds the critical value of 1, the fundamental mathematics change completely. The object no longer follows an elliptical path, but instead traces a hyperbolic trajectory, like the distinctive arms of a mathematical hyperbola stretching toward infinity. At 6.3, 3I Atlas follows one of the most open hyperbolic trajectories theoretically possible, barely influenced by our Sun's gravitational field. This extreme mathematical value provides crucial information about the object's violent past. Such extraordinarily high eccentricity typically results from close encounters with massive gravitational sources, catastrophic perturbations that accelerate objects far beyond their normal escape velocities. Think of a marble rolling peacefully around the edge of a bowl, then suddenly being struck so violently that it flies completely out of the container and across the room. The precise trajectory calculations also reveal exactly where 3I Atlas entered our solar system. It arrived from the direction of the constellation Sagittarius, coming from the general area of the galactic center where star density reaches its highest concentrations. This incoming path suggests the object may have encountered multiple gravitational influences during its long interstellar journey, with each close stellar passage slightly altering its course through space. Astronomers can now predict with remarkable precision exactly where 3I Atlas will travel during its brief visit to our cosmic neighborhood. The mathematics show it will reach perihelion, its closest approach to the Sun, on October 29th, passing just 1.4 astronomical units from our star. This distance places it safely inside the orbit of Mars, but comfortably far from Earth's position. Yet this mathematical precision opens profound new questions about what cosmic violence created such an extreme wanderer. While professional astronomers focus their attention on current observations and trajectory calculations, amateur researchers were already quietly rewriting the entire discovery story of 3I Atlas. The true heroes of this remarkable detection include ordinary people with extraordinary dedication to uncovering cosmic truths hidden in plain sight. Sam Dean, working methodically from his home computer setup, systematically began searching through archived Atlas telescope data spanning many weeks before the official discovery announcement. His patient persistence and careful attention to detail paid off spectacularly when he found clear, unmistakable images of the mysterious object from June 25th through 29th, extending the crucial observation timeline by several vital days. These pre-discovery observations completely transformed rough preliminary estimates into precise mathematical calculations. With additional data points spanning a much longer time frame, astronomers could dramatically refine the orbital parameters, confirming the object's interstellar origin with absolute mathematical certainty. What had started as tentative suggestions based on limited data became undeniable proof of an alien visitor. Other dedicated citizen scientists quickly contributed their own remarkable discoveries to the growing body of evidence. Yi Quanji methodically located observations from the Zwicky Transient Facility's archives dating all the way back to June 14th, while accomplished amateur astronomer Philip Romanov captured stunning confirmation images using sophisticated remote telescope systems located in Chile. Their collective effort created the most comprehensive tracking record ever assembled for an interstellar object. This unprecedented collaboration represents a revolutionary new era in astronomical research, where professional observatories and passionate amateur researchers work together seamlessly to uncover cosmic mysteries that might otherwise remain hidden. The democratization of telescope access through remote observing systems and the availability of public data archives now allows anyone with sufficient curiosity and patience to make genuine, meaningful contributions to cutting-edge science. The citizen science movement also highlights how easily extraordinary objects can hide in plain sight within massive datasets. 3I Atlas had actually appeared in multiple different telescope surveys for weeks before anyone recognized its true extraterrestrial nature. Only through painstaking analysis and careful cross-referencing of observations did its remarkable interstellar identity finally emerge from the data. This crucial detective work proved absolutely essential because 3I Atlas had nearly escaped detection entirely, effectively camouflaged against one of the most challenging observational backgrounds in the entire night sky. Without the dedicated efforts of these amateur astronomers, this cosmic visitor might have passed through our solar system completely unnoticed. The collaborative spirit demonstrated by these citizen scientists showcases the power of distributed research and the democratization of astronomical discovery in the 21st century. 3I Atlas almost became the greatest interstellar visitor that got away. For crucial weeks, it traveled steadily through our solar system completely unnoticed by automated detection systems, not because it was too faint or moving too slowly, but because it was hiding in the absolute worst possible location for astronomical observations. The object's orbital path carried it directly in front of the galactic center, the incredibly dense heart of our Milky Way galaxy, where billions upon billions of stars create a brilliant, overwhelmingly crowded backdrop. Imagine trying to spot a single snowflake during the height of a fierce blizzard, and you begin to understand the monumental challenge that confronted astronomers attempting to detect moving objects in this region. This area of sky toward the constellation Sagittarius contains the highest concentration of visible stars anywhere on Earth's night sky. The massive galactic bulge creates such an extraordinarily dense stellar field that distinguishing individual moving objects from the static background stars becomes almost impossibly difficult. Automated detection systems, specifically designed and optimized to spot moving objects against relatively empty star fields, struggle tremendously in these visually chaotic regions. Sam Dean, the citizen scientist who eventually found the crucial pre-discovery observations, noted that 3I Atlas likely remained undetected for such an extended period precisely because of this cosmic camouflage effect. The visitor blended almost seamlessly with the overwhelming stellar background, its subtle motion completely masked by the visual chaos created by countless distant suns, all competing for attention. The profound irony of this situation cannot be overstated. 3I Atlas arrived from the general direction of the galactic center, potentially carrying invaluable scientific information about star formation processes and planetary system evolution from that incredibly dynamic and active region of our galaxy. Yet its very origin among the dense star fields made detection nearly impossible using current automated survey techniques. The galactic center region presents unique observational challenges that extend far beyond simple star density. Interstellar dust clouds scatter and absorb light, creating complex patterns of brightness and darkness that can confuse automated detection algorithms. Gravitational lensing effects from massive objects can distort the apparent positions of background stars, making it even more difficult to identify genuinely moving objects. Only when 3I Atlas finally moved away from the densest concentration of background stars did automated survey systems begin flagging it as potentially unusual. By that time, precious weeks of potential observation time had already been lost forever, though fortunately enough remained for comprehensive scientific study. This near miss highlights a crucial and previously unrecognized limitation in our current detection capabilities and survey strategies. When the enigmatic object Oumuamua first appeared in our solar system during 2017, it immediately sparked intense scientific debate and increasingly wild speculation among researchers worldwide. Its strange, unexplained acceleration away from the Sun, highly unusual elongated shape, and complete lack of visible cometary activity led some prominent researchers to propose increasingly exotic explanations, including the genuinely controversial possibility of artificial origin. 3I Atlas presents an entirely different and refreshingly straightforward story. This latest interstellar visitor behaves exactly as astronomers expect a typical interstellar comet should behave, following completely predictable physics without any mysterious accelerations, unexplained trajectory changes, or other puzzling properties that might suggest exotic origins. Early observational data revealed unmistakable signs of normal cometary activity that matched theoretical predictions perfectly. Multiple telescopes detected a faint but clearly visible coma, the characteristic cloud of gas and dust that naturally surrounds active comets as they approach closer to the Sun and begin experiencing significant solar heating. The object also displayed a short but distinct tail, measuring just 3 arcseconds in angular length, definitively confirming its status as a genuine comet rather than an inert, rocky asteroid. The prestigious Nordic Optical Telescope observations conducted by renowned astronomers David Jewett and Jane Liu provided conclusive evidence that 3I Atlas was clearly and unmistakably active, steadily releasing gas and dust material as solar heating began affecting its ancient icy nucleus. This completely normal behavior matches detailed theoretical predictions for exactly how interstellar comets should appear when entering a new star system after millions of years in deep space. Unlike Oumuamua's deeply puzzling reddish surface coloration and bizarre cigar-like shape that defied easy explanation, 3I Atlas exhibits all the expected properties of a comet that formed naturally in the cold outer regions of another planetary system billions of years ago. Its overall composition and behavior appear remarkably similar to comets found in our own Kuiper belt, strongly suggesting common formation processes occur across many different star systems throughout the galaxy. Detailed measurements from the Fox Telescope North revealed that the comet's surrounding coma displays a distinctly reddish color, clearly indicating significant dust content, remarkably similar to the previous interstellar comet Borisov discovered in 2019. This important consistency strongly supports current theoretical models of how planetary systems form and evolve around different types of stars. 3I Atlas represents exactly what scientists hope to find: more interstellar objects that can teach us fundamental truths about the universe through familiar, well-understood physics, rather than baffling mysteries that challenge our basic understanding of how the cosmos works. Yet even this refreshingly well-behaved cosmic visitor faces the inevitable challenge of extremely limited observation time. From the precise moment 3I Atlas received official confirmation as a genuine interstellar visitor, astronomers worldwide immediately launched into unprecedented coordinated action. Every major telescope facility on Earth began urgently requesting emergency observation time, knowing they faced only an extremely narrow window of opportunity before this cosmic visitor disappeared forever into the depths of space. The urgent time pressure stems directly from 3I Atlas's specific trajectory and unfortunate timing relative to Earth's position. The comet will remain observable from ground-based telescopes only through September 2025, after which it passes dangerously close to the Sun for safe telescope observations. Intense solar glare will then completely hide the object until early December, when it finally re-emerges on the far side of our star, already beginning its inexorable exit from the solar system. Professional observatories spanning the globe from Chile's Atacama Desert to Hawaii's Mauna Kea are now dedicating their most precious telescope time to studying this remarkable cosmic messenger. The James Webb Space Telescope, humanity's most powerful infrared observatory, has already begun turning its sophisticated instruments toward 3I Atlas to analyze its thermal emissions and detailed chemical composition with unprecedented precision. The European Southern Observatory facilities scattered across Chile, including the world-renowned Very Large Telescope Array, are systematically tracking the object's brightness variations and conducting detailed spectroscopic studies. These crucial observations will reveal exactly what chemical elements and molecular compounds make up the comet's ancient nucleus and active coma, providing invaluable clues about environmental conditions in its distant birth system. Ground-based telescopes face significant additional technical challenges beyond simple time constraints. 3I Atlas currently appears at magnitude 18.8, requiring sophisticated equipment and exceptionally dark skies for successful detection. While it may brighten slightly as it approaches closer to the sun, it will never become visible to casual stargazers or amateur observers using basic equipment. The remarkable collaborative effort extends far beyond professional observatory facilities. Amateur astronomers equipped with advanced imaging systems are contributing valuable photometric observations, particularly crucial measurements that track subtle brightness variations and help determine the object's rotation period and surface properties. This extraordinary international cooperation represents modern astronomy at its absolute finest, with researchers freely sharing data and carefully coordinating observations to maximize scientific return from this incredibly rare opportunity. Never before have so many telescopes simultaneously focused on a single interstellar visitor. The Lowell Observatory's Discovery Telescope in Arizona has been conducting nightly observations since the Discovery announcement, while observatories in Australia and South Africa provide crucial southern hemisphere coverage as the object moves across different regions of sky. But the real excitement comes from the remarkable discoveries these coordinated observations are already beginning to reveal. As 3I Atlas races steadily toward the inner reaches of our solar system, it is undergoing a truly remarkable and unprecedented transformation. After spending millions of years in the absolutely frigid depths of interstellar space, this ancient comet is slowly beginning to awaken as our sun's increasingly intense energy finally reaches its primordial surface for the first time in eons. The very first signs of renewed activity appeared almost immediately after the initial discovery announcement. Sensitive telescopes quickly detected the gradual formation of a distinctive coma, the characteristic bright cloud of gas and dust that naturally forms when solar heating starts sublimating ancient ice deposits directly from the comet's nucleus. This fascinating process transforms solid ice directly into vapor, completely bypassing the liquid phase, entirely due to the vacuum conditions of space. The comet's newly formed tail, though currently only 3 arcseconds in angular size when viewed from Earth, represents precious material streaming steadily away from the nucleus, under relentless pressure from solar radiation and the constant solar wind. As 3I Atlas continues its approach toward the Sun over the coming months, this tail will almost certainly grow dramatically longer and more visually prominent. What makes this cosmic awakening particularly fascinating from a scientific perspective is that it represents the very first time in millions of years that this ancient object has experienced any significant heating whatsoever. During its incredibly long journey through the vast emptiness of interstellar space, 3I Atlas was constantly exposed to temperatures approaching absolute zero, with only the extremely faint radiation from distant stars providing any measurable energy input. The dramatic transition from deep space cold to intense solar heating triggers remarkably complex chemical and physical processes throughout the comet's structure. Subsurface ice deposits begin sublimating at various depths, potentially exposing completely fresh material that has remained essentially unchanged since the comet's original formation billions of years ago in an entirely different star system. Sophisticated spectroscopic observations are already beginning to reveal the detailed chemical composition of the escaping gases and dust. These precise measurements will tell scientists exactly what molecules and chemical compounds make up the comet's ancient nucleus, providing direct samples of pristine material from another planetary system billions of light years away. The subtle brightness variations that astronomers are carefully monitoring may eventually reveal how the nucleus rotates and whether its surface displays uniform composition throughout. Some areas might prove significantly more active than others, creating dramatic jets of gas and dust as they rotate to face the sun during the comet's approach. This remarkable awakening process offers an absolutely unique scientific opportunity to study completely pristine material from beyond our solar system. The distinctly reddish glow now surrounding 3I Atlas tells an ancient story written in cosmic dust particles, revealing precious secrets about its mysterious origin and the incredibly long journey through the cold depths of interstellar space. This subtle but unmistakable color signature provides crucial scientific clues about the comet's detailed composition and complex evolutionary history. Careful observations, conducted by the Fox Telescope North, clearly show that the comet's developing coma displays a distinctly reddish hue, definitively indicating the presence of complex organic compounds and various dust particles throughout the surrounding cloud. This characteristic coloration closely resembles that observed around Borisov, the previous interstellar comet discovered in 2019, strongly suggesting fundamentally similar formation processes occurred in the cold outer regions of different planetary systems. The ancient dust, now being steadily released from 3I Atlas's nucleus, contains invaluable scientific information about environmental conditions in its birth system that existed billions of years ago. When planetary systems first form around young stars, the frigid outer regions naturally become populated with countless icy bodies rich in water, carbon dioxide, methane, and complex organic molecules. These fundamental building blocks of planets and potentially life itself become incorporated into comets during the violent, chaotic early phases of planetary system evolution. Detailed spectroscopic analysis of the escaping dust reveals specific wavelengths of light that are characteristically absorbed and emitted by different chemical compounds. Each individual molecule possesses a unique spectral fingerprint, allowing skilled astronomers to identify water vapor, carbon monoxide, methane, ammonia, and increasingly complex organic species within the expanding coma surrounding the nucleus. The precise size distribution of dust particles also provides critically important scientific information about the comet's activity levels. Larger particles typically indicate very recent activity directly from the nucleus surface, while much smaller grains may have been gradually processed by cosmic radiation during the extended interstellar journey. The observed ratio between different particle sizes helps determine how geologically active the comet was in its original star system versus how much new material is being released now. Upcoming infrared observations will prove particularly valuable for studying the detailed thermal properties of individual dust grains. The James Webb Space Telescope can detect subtle heat radiation emitted by microscopic dust particles, revealing their precise temperature, size distribution, and chemical composition, with completely unprecedented accuracy and detail. The European Southern Observatory's Very Large Telescope is conducting complementary studies using advanced polarimetry techniques to understand how dust particles scatter sunlight, providing additional insights into their shape, size, and internal structure. This cosmic dust represents some of the most scientifically pristine material we can possibly study from another star system. Next, we explore why this visitor appears to be dramatically larger than any previous interstellar objects. Ice from the comet's nucleus. This process transforms solid ice directly into vapor, bypassing the liquid phase entirely. The comet's short tail, though only 3 arcseconds in angular size, represents material streaming away from the nucleus under pressure from solar radiation and the solar wind. As 3I Atlas continues approaching the sun, this tail will likely grow longer and more prominent. What makes this awakening particularly fascinating is that it represents the first time in millions of years that this object has experienced significant heating. During its long journey through interstellar space, 3I Atlas was exposed to temperatures near absolute zero, with only the faint radiation from distant stars providing any energy input. The transition from deep space cold to solar heating triggers complex chemical and physical processes. Subsurface ices begin sublimating, potentially exposing fresh material that has remained unchanged since the comet's formation billions of years ago in another star system. Spectroscopic observations are already revealing the composition of the escaping gases. These measurements will tell us what molecules and compounds make up the comet's nucleus, providing direct samples of material from another planetary system. The brightness variations astronomers are monitoring may reveal how the nucleus rotates and whether its surface has uniform composition. Some areas might be more active than others, creating jets of gas and dust as they face the sun. This awakening process offers a unique opportunity to study pristine material from beyond our solar system. The reddish glow surrounding 3I Atlas tells a story written in cosmic dust, revealing secrets about its origin and the long journey through interstellar space. This color signature provides crucial clues about the comet's composition and history. Observations from the Fox telescope north show the comet's coma displays a distinctly reddish hue, indicating the presence of complex organic compounds and dust particles. This coloration closely resembles that of Borisov, the previous interstellar comet, suggesting similar formation processes in the outer regions of planetary systems. The dust being released from 3I Atlas nucleus contains information about conditions in its birth system billions of years ago. When planetary systems form, the outer regions become populated with icy bodies, rich in water, carbon dioxide, and organic molecules. These building blocks of planets and life get incorporated into comets during the chaotic early phases of system evolution. Spectroscopic analysis of the dust reveals specific wavelengths of light absorbed and emitted by different compounds. Each molecule has a unique spectral fingerprint, allowing astronomers to identify water vapor, carbon monoxide, methane, and more complex organic species in the coma. The size and distribution of dust particles also provide important information. Larger particles indicate recent activity from the nucleus, while smaller grains may have been processed by radiation during the long interstellar journey. The ratio between different particle sizes helps determine how active the comet was in its original system versus how much material is being released now. Infrared observations will be particularly valuable for studying the thermal properties of the dust. The James Webb Space Telescope can detect heat radiation from dust grains, revealing their temperature, size, and composition with unprecedented precision. This cosmic dust represents some of the most pristine material we can study from another star system, carrying chemical signatures from a time and place billions of years and light years removed from Earth. Next, we explore why this visitor appears to be dramatically larger than previous interstellar objects. 3I Atlas represents a dramatic departure from our previous encounters with interstellar visitors, particularly in terms of its potentially enormous size. Current estimates suggest this cosmic wanderer could be 10 times larger than any interstellar object we have previously detected, fundamentally changing our understanding of what kinds of objects regularly travel between star systems. Initial brightness measurements indicate 3I Atlas has an absolute magnitude of approximately 11.9, which translates to a maximum possible diameter of around 24 kilometers if it were a dark, inactive asteroid. However, because this object is clearly an active comet surrounded by a bright, reflective coma of gas and dust, the actual size of its solid nucleus is expected to be significantly smaller than these initial estimates suggest. Nevertheless, even conservative calculations suggest 3I Atlas appears to be substantially larger than both previous interstellar visitors. The mysterious Oumuamua measured only a few hundred meters across at most, while comet Borisov's nucleus was estimated at just 400 to 500 meters in diameter. If current size estimates prove accurate, 3I Atlas could represent an entirely different class of interstellar object. This dramatic size difference raises profound questions about the processes that eject objects from their home planetary systems. Larger objects require significantly more energy to achieve the escape velocities necessary for interstellar travel. The fact that something this massive was accelerated to such extreme speeds suggests incredibly violent cosmic events occurred in its birth system. The larger size also has important implications for the object's scientific value. Bigger comets typically contain more diverse chemical compositions and retain better records of their formation conditions. 3I Atlas may preserve pristine samples of material from multiple regions of its original planetary system, offering unprecedented insights into alien world formation. Determining the exact size remains challenging because active comets are surrounded by expanding clouds of reflective dust that can dramatically increase their apparent brightness. The true nucleus could be much smaller than current estimates suggest, hidden within the growing coma that makes precise measurements extremely difficult using current observational techniques. Advanced radar observations might eventually provide more accurate size measurements by penetrating the dusty coma to directly detect the solid nucleus beneath. The Archival Observatory's replacement facilities and other major radar installations are being considered for this challenging but potentially rewarding observational campaign. The James Webb Space Telescope's infrared capabilities offer another avenue for determining accurate size measurements. By detecting thermal emissions from the nucleus itself, astronomers can distinguish between heat coming from the solid core versus reflected sunlight from the surrounding dust cloud. Understanding the true size of 3I Atlas will help astronomers better model the population of interstellar objects and predict how many similar visitors we might expect to discover in the coming years. The discovery of 3I Atlas coincides perfectly with the beginning of a revolutionary new era in astronomical surveying, marked by the recent activation of the Vera C Rubin Observatory in Chile. This remarkable facility promises to transform our ability to detect interstellar visitors from rare, accidental discoveries into routine scientific observations. The Rubin Observatory represents the most advanced sky survey system ever constructed, designed specifically to scan the entire southern sky repeatedly every few nights for an entire decade. Its massive 3.2 gigapixel camera captures images covering 3.5 degrees of sky in just 15 seconds, wide enough to fit 7 full moons side by side in a single frame. During its first week of operation, the observatory discovered over 200 previously unknown asteroids, demonstrating its extraordinary capability for finding moving objects. This detection rate far exceeds what all other ground and space-based observatories combined typically discover in an entire year, suggesting a fundamental shift in our observational capabilities. The automated systems can identify potentially interesting objects within minutes of capturing an image, comparing new observations with previous data to flag anything that moves, brightens, or exhibits unusual behavior. This rapid processing capability means interstellar visitors like 3I Atlas would be detected and tracked from their very first appearance in our solar system. Current estimates suggest the Rubin Observatory will discover between 1 and 10 interstellar objects every year once it reaches full operational capacity. This represents a dramatic increase from the current rate of roughly 1 discovery every few years, potentially providing a steady stream of cosmic visitors for detailed study. The observatory's wide field of view and rapid scanning capability will also help solve the detection bias problems that nearly caused 3I Atlas to go unnoticed. Even objects passing through crowded star fields near the galactic center will be detectable using sophisticated image processing algorithms designed to identify subtle motion patterns. The facility's unprecedented data collection rate will generate approximately 20 terabytes of information every night, requiring advanced artificial intelligence systems to identify the most scientifically interesting targets among millions of routine observations. This technological revolution means the era of interstellar visitors, as rare, unexpected discoveries, is rapidly coming to an end. Instead, these cosmic messengers will become regular subjects of scientific investigation, allowing astronomers to build comprehensive understanding of how planetary systems throughout the galaxy form, evolve, and eventually release objects into interstellar space. The statistical sample of interstellar objects will grow large enough to answer fundamental questions about the structure and evolution of planetary systems around different types of stars. The journey of 3I Atlas through interstellar space represents one of the most extreme survival stories in the known universe. For millions of years, this ancient comet has endured conditions that would instantly destroy most materials we encounter on Earth. Yet, it has emerged from this cosmic ordeal essentially intact and ready to tell its story. During its extended voyage between star systems, 3I Atlas experienced temperatures approaching absolute zero, approximately -270 degrees Celsius. At these extreme temperatures, most chemical reactions completely cease, and materials become incredibly brittle. The thermal energy available is so minimal that even the motion of individual atoms within molecules slows to nearly imperceptible levels. The radiation environment of interstellar space presents equally challenging survival conditions. High-energy cosmic rays, accelerated to tremendous speeds by distant supernovae and other violent cosmic events, constantly bombarded the comet's surface. These energetic particles can break apart complex molecular structures and gradually alter the chemical composition of exposed materials over geological timescales. Galactic cosmic radiation includes everything from individual protons and electrons to heavy atomic nuclei, traveling at significant fractions of light speed. When these particles strike the comet's surface, they create cascades of secondary radiation that can penetrate several meters into solid ice and rock, potentially altering subsurface materials that will only be exposed when the comet becomes active again. Despite these harsh conditions, 3I Atlas appears to have retained its structural integrity and chemical composition remarkably well. The fact that it can still outgas normally when heated by our Sun suggests that its internal ice deposits remain largely uncontaminated by radiation damage or thermal cycling effects. The comet's ability to survive this cosmic odyssey intact provides valuable information about the resilience of materials under extreme conditions. Understanding how complex molecules and ice structures withstand millions of years of radiation exposure has important implications for astrobiology and the potential preservation of organic compounds in space environments. Theoretical models suggest that objects like 3I Atlas can maintain viable chemical compositions for tens of millions of years during interstellar travel, potentially carrying complex organic molecules and even simple biological precursors between star systems. This possibility raises fascinating questions about whether life itself might occasionally spread through the galaxy via interstellar objects. The surface layers that experience direct radiation exposure during the journey may have developed protective crusts that actually helped preserve underlying materials from further damage, creating natural time capsules of pristine ancient material. The incoming trajectory of 3I Atlas provides tantalizing clues about its ultimate origin, potentially allowing astronomers to trace this cosmic wanderer back through millions of years of galactic motion to identify its probable birth system. This astronomical detective work represents one of the most ambitious forensic investigations ever attempted in space science. The comet arrived from the direction of Sagittarius, specifically from the galactic disk region, where the majority of stars in our Milky Way galaxy reside. This directional information, combined with its extreme velocity and trajectory calculations, suggests 3I Atlas has been traveling through space for several million years since its violent ejection from its home system. Reconstructing the object's path requires accounting for the complex gravitational influences it encountered during its journey. Our galaxy rotates like a massive pinwheel, with different regions moving at different speeds relative to each other. Stars closer to the galactic center orbit faster than those in the outer regions, creating a dynamic environment where stellar neighborhoods constantly change over time. During its multi-million-year journey, 3I Atlas would have passed through regions containing hundreds or thousands of different star systems. Each close approach to a massive object would have slightly altered its trajectory, making precise backtracking extremely challenging, but not impossible with sophisticated computer modeling. The comet's current velocity vector, when extrapolated backward through galactic space while accounting for known stellar motions, suggests it may have originated from a region that was much closer to our solar system several million years ago. The relative motion of star systems means that 3I Atlas's birth star could now be located in a completely different part of the galaxy. Advanced computer simulations can model the gravitational environment of the local galactic neighborhood over extended time periods, incorporating data about stellar positions, masses, and velocities to reconstruct possible trajectories. These calculations require enormous computational resources, but can potentially identify candidate star systems that were positioned appropriately to eject an object along 3I Atlas's observed path. Several research groups are already beginning this complex analysis, using data from the European Space Agency's Gaia spacecraft, which has precisely measured the positions and motions of over 1 billion stars throughout our galaxy. This unprecedented stellar catalogue provides the foundation for tracing interstellar objects back to their origins. The investigation faces significant challenges due to measurement uncertainties and the chaotic nature of gravitational interactions over such extended time periods. Small errors in initial conditions can lead to dramatically different conclusions about the object's origin, requiring careful statistical analysis of multiple possible scenarios. Successfully identifying 3I Atlas's birth system would represent a breakthrough in understanding how planetary systems evolve and how material gets exchanged between different star systems throughout the galaxy. The extreme velocity of 3I Atlas tells a story of catastrophic violence that occurred millions of years ago in a distant star system. Objects don't naturally achieve the tremendous speeds necessary for interstellar travel through gentle evolutionary processes. They require sudden, powerful gravitational encounters that can instantly transform ordinary comets into cosmic bullets racing through the galaxy. Several different scenarios could have provided the enormous energy needed to accelerate 3I Atlas to its current 66 kilometers per second velocity. The most likely explanation involves close encounters with massive objects during the chaotic early evolution of its birth planetary system, when large planets were still migrating and interactions between multiple bodies created dynamically unstable conditions. Gravitational slingshot effects around giant planets can accelerate smaller objects to extremely high velocities under the right circumstances. When a comet approaches a massive planet on a carefully angled trajectory, it can gain tremendous energy from the planet's orbital motion, effectively stealing momentum from the much more massive world and redirecting it into escape velocity. Multiple sequential encounters with different planets can create even more dramatic acceleration effects, with each gravitational interaction adding more energy to the object's motion. Computer simulations show that objects can occasionally achieve hyperbolic escape trajectories through a series of precisely timed planetary encounters that occur during periods of orbital instability. Another possibility involves stellar close encounters, where a passing star approaches close enough to gravitationally disrupt the outer regions of 3I Atlas's birth system. When two star systems pass within a few light years of each other, their gravitational fields can interact to fling objects from the outer reaches of planetary systems into interstellar space at tremendous velocities. The most dramatic ejection mechanism involves stellar evolution itself. When massive stars reach the end of their lives and undergo supernova explosions, the tremendous energy release can accelerate nearby objects to significant fractions of light speed. While 3I Atlas's velocity is far below such extreme levels, asymmetric supernova explosions or interactions with stellar remnants could potentially provide the necessary acceleration. Binary star systems offer additional ejection possibilities. When two stars orbit closely together, objects in the outer regions of such systems can experience complex gravitational effects that occasionally result in hyperbolic ejection trajectories. The gravitational dance between multiple massive objects creates chaotic dynamics that can unpredictably accelerate smaller bodies. Recent theoretical work suggests that planetary system instabilities during the late heavy bombardment period, similar to what our own solar system experienced billions of years ago, routinely eject significant numbers of objects into interstellar space. Understanding these ejection mechanisms helps astronomers estimate how many interstellar objects should be traveling through our galaxy at any given time. 3I Atlas represents far more than just another interesting astronomical object. It serves as a direct physical sample from an entirely different planetary system, carrying invaluable information about how worlds form and evolve around distant stars. This cosmic messenger offers a unique opportunity to study alien chemistry and geology without the impossible challenge of traveling to other star systems. Comets form in the cold outer regions of planetary systems, where temperatures are low enough for water, carbon dioxide, methane, and other volatile compounds to freeze into solid ice. They incorporate materials from multiple sources, During the chaotic early phases of planetary system formation, including dust grains from the original stellar nebula, processed materials from the inner system, and organic compounds created through various chemical processes. The chemical composition of 3I Atlas's nucleus and coma will reveal fundamental information about the elemental abundances and isotopic ratios present in its birth system. Different stars have different metallicities and chemical signatures based on their formation history and stellar evolution, creating distinct fingerprints that should be preserved in objects that formed around them. Spectroscopic analysis can identify specific molecules and compounds being released from the comet's nucleus as it approaches the Sun. Water vapor, carbon monoxide, carbon dioxide, methane, ammonia, and more complex organic species each have characteristic spectral signatures that allow astronomers to determine not only what elements are present, but also how they're chemically bonded together. Isotopic ratios provide particularly valuable information about stellar nucleosynthesis processes and the chemical evolution of the galaxy. The relative abundances of different isotopes of elements like carbon, nitrogen, and oxygen can reveal details about the stellar environment where 3I Atlas formed and whether its birth system experienced unusual stellar evolution events. Organic compounds are of special interest because they provide insights into the potential for life in other planetary systems. While 3I Atlas likely formed too far from its host star to have directly supported life, it may contain complex, carbon-based molecules that represent the building blocks from which life could potentially emerge under more favorable conditions. The dust particles being released from the comet's nucleus offer another avenue for studying alien materials. These microscopic grains can preserve information about high-temperature processes that occurred during the early formation of the planetary system, including condensation sequences and thermal processing in the inner regions before being transported outward. Advanced laboratory techniques, if samples could somehow be collected, would allow incredibly detailed analysis of individual dust grains and ice crystals. However, even remote spectroscopic observations can provide remarkably detailed information about the composition and structure of materials from another star system. Comparing 3I Atlas's composition with objects in our own solar system will reveal similarities and differences that reflect the universal versus unique aspects of planetary system formation and chemical evolution. Time is rapidly running out for humanity's investigation of 3I Atlas, creating an unprecedented sense of urgency among the global astronomical community. This interstellar visitor offers a once-in-a-generation opportunity to study pristine material from another star system, but the window for comprehensive observations is closing faster than many scientists would prefer. The primary challenge stems from 3I Atlas's specific orbital mechanics and its relationship to Earth's position around the Sun. As the comet continues its approach toward perihelion in late October, it will pass increasingly close to the Sun's position in our sky, making telescopic observations progressively more difficult due to solar glare and interference. Ground-based observatories face the additional constraint that 3I Atlas must be observed during nighttime hours when the object is above the horizon and the sky is sufficiently dark. As the comet's apparent position moves closer to the Sun, the available observing window each night becomes shorter and shorter, ultimately disappearing entirely when the object passes behind the Sun from Earth's perspective. The situation is further complicated by seasonal effects and the geographic distribution of major observatories. Northern Hemisphere facilities are losing access to 3I Atlas as its declination carries it further south, while Southern Hemisphere observatories must contend with increasing solar interference as the object approaches perihelion. Space-based telescopes offer some advantages over ground-based facilities, particularly the ability to observe during Earth's daytime hours when ground telescopes cannot function. However, even space observatories must carefully avoid pointing too close to the Sun to prevent damage to sensitive instruments, limiting their ability to track 3I Atlas during its closest solar approach. The James Webb Space Telescope, positioned at the L2 Lagrange point, has a better geometric arrangement for continuing observations later into the comet's approach, but it too faces constraints on how close to the Sun it can safely point its instruments. mission planners are carefully optimizing observing schedules to maximize scientific return while protecting the valuable facility. After disappearing behind the Sun in late September, 3I Atlas will remain unobservable for several months before re-emerging in December on the opposite side of our star. By that time, the comet will already be racing away from the inner solar system, growing fainter and less active as it retreats into the cold depths of space beyond. The December reappearance offers a second chance for observations, but the comet will be significantly fainter and less active than during its inbound approach. Many of the detailed spectroscopic measurements that require high signal-to-noise ratios may become impossible once the object begins its outbound journey. This timing constraint means that the next few months represent humanity's only realistic opportunity to conduct comprehensive studies of this remarkable interstellar visitor. The James Webb Space Telescope represents humanity's most powerful tool for studying 3I Atlas, offering unprecedented capabilities for analyzing the thermal properties and chemical composition of this interstellar visitor. Webb's advanced infrared instruments can detect heat radiation and molecular signatures that remain completely invisible to optical telescopes, opening entirely new avenues for understanding alien materials. Infrared observations provide crucial advantages for studying active comets because many important molecular species emit characteristic radiation at infrared wavelengths. Water vapor, carbon monoxide, carbon dioxide, methane, and numerous organic compounds all have distinctive infrared spectral signatures that Webb's sophisticated instruments can detect and analyze with remarkable precision. The telescope's near-infrared spectrograph can simultaneously observe hundreds of different wavelengths, creating detailed spectral maps that reveal the presence and abundance of numerous chemical species within 3I Atlas's coma. This capability allows astronomers to construct comprehensive chemical inventories that would be impossible using any other existing facility. Webb's mid-infrared instrument offers complementary capabilities for studying the thermal properties of dust particles being released from the comet's nucleus. By measuring the infrared heat radiation emitted by microscopic grains, astronomers can determine their temperature, size distribution, and composition with unprecedented accuracy. The thermal measurements also provide insights into the comet's internal structure and activity patterns. Different regions of the nucleus may heat up at different rates as the comet approaches the Sun, creating temperature variations that can reveal information about the object's rotation, surface composition, and subsurface thermal properties. One of Webb's most valuable capabilities involves detecting extremely faint infrared emission lines from trace species that might be present in tiny quantities within the comet's atmosphere. These measurements could potentially identify complex organic molecules or unusual isotopic ratios that provide clues about exotic chemical processes in the birth system. The telescope's exceptional stability and sensitivity allow for time series observations that track how 3I Atlas's activity changes as it approaches the Sun. These temporal measurements can reveal how different chemical species respond to increasing solar heating, providing insights into the physical structure and composition of the nucleus. Webb's infrared capabilities also enable observations that penetrate through the dusty coma to study thermal emission from the nucleus itself. This direct view of the solid core can provide size estimates and surface temperature measurements that are impossible to obtain using optical wavelengths where dust scattering dominates the observed brightness. Coordinated observations using Webb's multiple instruments can create comprehensive portraits of 3I Atlas that combine chemical analysis, thermal mapping, and temporal monitoring into unified scientific datasets. These integrated measurements will provide the most detailed characterization ever achieved for an interstellar object. The telescope's position at the L2 Lagrange point also provides advantageous geometry for extended observations of 3I Atlas as it approaches and passes perihelion. The subtle variations in brightness that 3I Atlas displays as it rotates provide a cosmic barcode that encodes crucial information about its shape, surface properties, and internal structure. These carefully measured light curves represent one of the most accessible ways for astronomers to characterize the physical properties of this distant interstellar visitor using ground-based telescopes. As 3I Atlas spins on its axis, different regions of its surface alternately face toward and away from the Sun and Earth, creating periodic changes in the amount of reflected sunlight that reaches our telescopes. The specific pattern of these brightness variations depends on the object's rotation rate, axial orientation, surface composition uniformity, and overall shape characteristics. Spherical objects produce relatively modest brightness variations because their projected area remains nearly constant regardless of viewing angle. However, elongated or irregularly shaped objects can show dramatic brightness changes as they present different cross-sections to observers, potentially varying by factors of several magnitudes over a single rotation period. The rotation period itself provides insights into the object's structural integrity and formation history. Rapidly spinning objects must be relatively cohesive to avoid flying apart under centrifugal forces, while slowly rotating bodies may indicate loose gravitational binding or recent collision history that disrupted their angular momentum. 3I Atlas presents unique observational challenges for light curve analysis because its developing coma creates additional brightness contributions that vary independently of the nucleus rotation. The expanding cloud of gas and dust reflects sunlight and emits its own thermal radiation, potentially masking the subtle periodic signals from the underlying solid body. Advanced photometric techniques can partially separate these different brightness contributions by observing at multiple wavelengths simultaneously. The nucleus surface reflects sunlight with different spectral characteristics than the surrounding dust cloud, allowing skilled observers to isolate the rotation signature through careful spectral analysis. Professional and amateur astronomers worldwide are conducting coordinated photometric campaigns to measure 3I Atlas's brightness variations continuously over extended periods. These collaborative efforts provide temporal coverage that no single observatory could achieve alone, ensuring that rotation periods spanning hours or days can be accurately determined. The brightness measurements also reveal information about surface composition heterogeneity. If different regions of the nucleus have varying reflectivity properties due to compositional differences or varying degrees of dust coverage, these variations will create characteristic patterns in the observed light curves. Comparing 3I Atlas's rotation properties with those of comets in our own solar system can reveal similarities and differences that reflect universal versus unique aspects of comet formation and evolution processes. These comparisons help astronomers understand whether interstellar objects represent fundamentally different populations or simply displaced versions of familiar solar system bodies. Long-term monitoring throughout the comet's approach to perihelion will track how increasing solar heating affects the rotation properties, potentially revealing asymmetric outgassing that could alter the spin rate or orientation over time. Despite its tremendous velocity and alien origin, 3I Atlas poses absolutely no danger to Earth or any other planet in our solar system. The comet's trajectory has been calculated with extraordinary precision, confirming that it will pass safely through the inner solar system without coming anywhere near our planet or disrupting any existing orbital dynamics. The closest approach to Earth will occur on December 17th, when 3I Atlas reaches a distance of approximately 2.4 astronomical units from our planet. This separation equals roughly 360 million kilometers, or about 2.5 times the distance between Earth and the Sun. At this range, the comet appears as nothing more than an extremely faint point of light requiring sophisticated telescopes for detection. Even during its closest approach to the Sun in late October, 3I Atlas will maintain a safe distance of 1.4 astronomical units, placing it well inside the orbit of Mars, but far from Earth's orbital path. This perihelion distance ensures that the comet experiences significant solar heating to drive its observable activity while remaining completely harmless to inner solar system dynamics. The comet's hyperbolic trajectory means it will never return to threaten Earth or any other world in our solar system. After completing its brief visit to the inner regions, 3I Atlas will continue racing outward into the depths of space, never to be seen again from our cosmic neighborhood. Its orbital energy far exceeds what would be needed for capture into a bound solar orbit. Planetary defense organizations worldwide have confirmed that 3I Atlas represents no impact risk whatsoever. The European Space Agency's Near-Earth Object Coordination Center and NASA's Planetary Defense Office both independently verified the safety calculations using multiple computational methods and observational datasets. The comet's relatively large size, while scientifically interesting, does not translate into any increased danger. Large objects, following safe trajectories, remain safe regardless of their dimensions, and 3.1 Atlas's path will carry it nowhere near any populated worlds or critical infrastructure in space. Ground-based radar systems that normally track potentially hazardous asteroids have also attempted to observe 3.1 Atlas, though its great distance and rapid motion make radar detection extremely challenging. These observations provide additional confirmation of the trajectory calculations while potentially revealing surface properties and rotation characteristics. The safety assurances allow the global astronomical community to focus entirely on the scientific opportunities presented by this remarkable visitor, without any concerns about planetary protection or impact mitigation. Research teams can dedicate their full attention to understanding what 3i Atlas reveals about interstellar objects and alien planetary systems. Public education efforts emphasize both the scientific excitement and complete safety of this cosmic encounter, helping to build support for continued astronomical research while avoiding unnecessary concerns about celestial threats. This combination of scientific importance and confirmed safety makes 3i Atlas an ideal ambassador for public engagement with space science. The discovery and characterization of 3.1 Atlas showcases the remarkable power of citizen science in modern astronomy, demonstrating how passionate amateur researchers can make crucial contributions to cutting-edge scientific investigations. This collaborative approach represents a fundamental shift in how astronomical discoveries unfold, democratizing participation in cosmic research beyond traditional academic institutions. Sam Dean's discovery of pre-discovery observations exemplifies the valuable role that dedicated amateurs can play in professional research. Working from his home computer with no formal institutional affiliation, Dean systematically searched through massive archival datasets that professional astronomers had not yet fully analyzed. His meticulous work extended 3.1 Atlas's observational timeline by crucial weeks, dramatically improving orbital calculations. The success of this citizen science approach reflects the increasing availability of professional quality astronomical data through online archives and public databases. Major survey projects like ATLAS, the Zwicky Transient Facility, and others routinely make their observations publicly accessible, creating opportunities for anyone with sufficient dedication and computational skills to make genuine discoveries. Amateur astronomers, equipped with modest but sophisticated equipment, are contributing valuable photometric observations of 3i Atlas from locations around the globe. These distributed measurements provide temporal coverage that no single professional observatory could achieve alone, enabling continuous monitoring of brightness variations and rotation properties. The democratization of telescope access through remote observing systems allows amateur researchers to use professional-grade instruments located in ideal dark sky locations. Services like iTelescope Net enables citizen scientists to capture high-quality images and spectroscopic data that contribute meaningfully to scientific understanding of interstellar objects. Social media platforms and online astronomy communities facilitate rapid information sharing and coordination among amateur observers worldwide. Within hours of 3i Atlas's discovery announcement, amateur astronomers were sharing observation plans, coordinate information, and preliminary results through networks that span multiple continents and time zones. The collaborative spirit extends beyond simple data collection to include sophisticated analysis techniques. Amateur researchers are developing innovative software tools for photometric analysis, astrometric measurements, and spectroscopic data reduction that rival capabilities available to professional institutions. Educational institutions are increasingly recognizing the value of citizen science projects for engaging students in authentic research experiences. High school and undergraduate astronomy programs are incorporating 3i Atlas observations into their curricula, providing students with opportunities to contribute to active scientific investigations while learning fundamental research techniques. The success of amateur contributions to 3.1 Atlas research helps validate the citizen science model for future astronomical discoveries. As automated sky surveys discover increasing numbers of interesting objects, the astronomical community will increasingly rely on distributed networks of amateur researchers to provide detailed follow-up observations and analysis. This collaborative approach maximizes the scientific return from limited professional telescope resources while engaging broader public audiences in the excitement of astronomical discovery. The successful detection and characterization of 3I Atlas represents a remarkable achievement that pushes current astronomical capabilities to their absolute limits. This interstellar visitor arrived at the very edge of what our existing telescope networks and detection systems can reliably observe, highlighting both the impressive capabilities and inherent limitations of 21st century space surveillance technology. At magnitude 18.8, 3I Atlas appears approximately 2.5 million times fainter than the North Star, requiring sophisticated equipment and exceptional observing conditions for successful detection. Most amateur telescopes cannot detect objects fainter than magnitude 15 or 16 under typical conditions, placing this interstellar visitor well beyond the reach of casual astronomical observation. The initial discovery by the Atlas survey system demonstrates the remarkable sensitivity of modern automated sky monitoring programs. Atlas routinely detects objects near magnitude 19, representing the current practical limit for wide-field survey telescopes that must cover large areas of sky efficiently while maintaining reasonable exposure times. Follow-up observations by larger telescopes push detection limits even further, with facilities like the Very Large Telescope capable of detecting objects several magnitudes fainter than survey systems. However, detailed spectroscopic analysis requires objects to be significantly brighter than the detection threshold, limiting the scientific information that can be extracted from extremely faint targets. The geometric circumstances of 3.1 Atlas's discovery were particularly challenging because the object appeared against the crowded star fields of the galactic center region. This background confusion significantly complicates automated detection algorithms that rely on identifying moving objects against relatively sparse stellar backgrounds. Weather conditions, atmospheric turbulence, and light pollution all significantly impact the ability to detect and track faint objects like 3I Atlas. Professional observatories invest enormous resources in site selection and environmental control systems to maximize their sensitivity to faint cosmic targets. The rapid motion of 3I Atlas across the sky presents additional technical challenges for obtaining detailed observations. Long exposure times normally used for studying faint objects become problematic when targets move significantly during the exposure, requiring specialized tracking techniques and shorter integration times that reduce overall sensitivity. Coordinated observations by multiple telescopes help overcome some of these limitations by combining data from different facilities to achieve better signal-to-noise ratios and more comprehensive coverage. International cooperation becomes essential for maximizing scientific return from challenging observational targets. The detection of 3.1 Atlas also highlights the importance of continuing technological development in astronomical instrumentation. Next-generation survey systems and space-based observatories will dramatically improve our ability to detect and study faint interstellar visitors, potentially revealing a much larger population of cosmic wanderers than current capabilities allow. Understanding detection limits helps astronomers estimate how many similar objects might be passing through our solar system undetected at any given time. The successful detection of 3I Atlas raises profound questions about how many similar interstellar objects might be quietly passing through our solar system completely unnoticed by current detection capabilities. Theoretical models suggest that the cosmos may be filled with far more cosmic wanderers than our limited observational experience would indicate. Statistical analysis of the 3 confirmed interstellar detections so far suggests that objects like 3I Atlas, Oumuamua, and Borisov represent only the tip of a much larger iceberg. For every interstellar visitor bright enough and well-positioned enough for detection by current survey systems, dozens or hundreds of similar objects likely pass through unobserved. The detection bias heavily favors objects that happen to pass relatively close to Earth and arrive from convenient directions in the sky. Interstellar visitors that traverse the outer regions of our solar system, approach from problematic viewing angles, or arrive during periods when Earth-based telescopes cannot observe them, will remain completely invisible to our detection networks. Current estimates suggest that at any given time, thousands of interstellar objects, larger than a few meters across, may be present within our solar system. The vast majority of these cosmic wanderers remain undetectable due to their small size, great distance, or unfavorable geometric circumstances for observation from Earth. The size distribution of interstellar objects likely follows similar patterns to asteroids and comets in our own solar system, with vastly more small objects than large ones. While 3I Atlas represents an unusually large specimen that aided its detection, the cosmic population probably consists primarily of much smaller bodies that current technology cannot reliably detect. Improvements in survey capability over the next decade will dramatically increase detection rates for interstellar objects. The Vera C. Rubin Observatory alone is expected to discover between 1 and 10 interstellar visitors annually once it reaches full operational capacity, representing a tenfold or greater increase over historical rates. Future space-based survey systems will further revolutionize interstellar object detection by eliminating atmospheric limitations and providing continuous sky coverage. These advanced facilities will be capable of detecting much fainter objects across wider areas of sky, potentially revealing the true abundance of cosmic wanderers. The hidden population of interstellar objects may include representatives from many different types of planetary systems throughout our galactic neighborhood. Each object carries unique information about its birth system, offering opportunities to study the chemical compositions and formation processes of worlds we cannot directly observe. Long-period surveys spanning decades will be necessary to build comprehensive statistical samples of interstellar objects and understand their diversity. The accumulated data will help astronomers understand ejection mechanisms, travel times, and the exchange of material between different star systems. Understanding the true population of interstellar visitors has important implications for planetary defense, astrobiology, and our understanding of how planetary systems evolve and interact throughout the galaxy. 3I Atlas serves as a direct sample of the fundamental building blocks that formed planets around a distant star, offering unprecedented insights into whether the processes that created worlds in our solar system represent universal patterns or unique local circumstances. This cosmic comparison reveals deep truths about planetary formation throughout the galaxy. The chemical composition being revealed through spectroscopic analysis of 3I Atlas's coma provides direct measurements of elemental abundances in another star system. These observations allow astronomers to compare the raw materials available for planet formation around different types of stars with varying ages, masses, and metallicities. Preliminary observations suggest 3I Atlas contains water, carbon monoxide, and other volatiles in proportions broadly similar to comets in our own Kuiper belt. This similarity supports theoretical models, suggesting that the basic chemistry of planetary formation follows universal physical laws, regardless of the specific stellar environment. However, subtle differences in isotopic ratios and trace element abundances may reveal important variations in stellar nucleosynthesis, processes, or galactic chemical evolution. The exact ratios of different isotopes of carbon, nitrogen, and oxygen can provide insights into the stellar generations that contributed material to 3I Atlas's birth system. The organic compounds being detected in the comet's atmosphere offer particular insights into prebiotic chemistry in alien environments. Complex carbon-based molecules form through various processes during planetary system evolution, and their presence or absence in interstellar objects reveals information about the potential for life in different cosmic environments. Dust grain analysis provides complementary information about high-temperature processes that occurred during the early formation of 3I Atlas's birth system. These microscopic particles preserve records of condensation sequences, thermal processing, and dynamical mixing that shaped the distribution of materials throughout the original planetary disk. Comparing 3I Atlas with meteorites and comets from our own solar system reveals both similarities and differences that illuminate the diversity of planetary system formation processes. Universal aspects reflect fundamental physics and chemistry, while unique characteristics reveal how local conditions influence world building. The size and activity level of 3I Atlas suggest it formed in the outer regions of a planetary system similar to our own, where temperatures were low enough for volatile compounds to condense into solid form. This environmental similarity supports the idea that habitable zone planets may be common throughout the galaxy. Understanding the relationship between stellar properties and the composition of ejected objects helps astronomers predict what types of materials might be available for planet formation around different categories of stars. This information is crucial for assessing the potential habitability of exoplanetary systems detected by survey missions. The accumulation of data from multiple interstellar objects will eventually allow comprehensive statistical comparisons between different stellar environments and their associated planetary building blocks. 3I Atlas represents far more than just another remarkable astronomical discovery. It heralds the beginning of a revolutionary new era in space exploration, where interstellar objects serve as natural spacecraft, delivering samples and information from distant worlds directly to our cosmic doorstep. This paradigm shift will fundamentally transform how humanity studies the galaxy and our place within it. The successful detection and characterization of this interstellar visitor demonstrates that our technological capabilities have finally reached the threshold necessary for routine interstellar object science. Advanced automated survey systems, sophisticated spectroscopic instruments, and coordinated global observation networks now provide the tools needed to extract maximum scientific value from these cosmic messengers. Future interstellar visitors will benefit from increasingly powerful observational capabilities as next-generation facilities come online over the next decade. The Vera C, Rubin Observatory, the extremely large telescope, and advanced space-based observatories will dramatically expand our ability to detect, track, and analyze objects from other star systems with unprecedented detail and precision. Each new interstellar object will add crucial data points to our growing understanding of planetary system formation, stellar evolution, and galactic chemical evolution. The accumulation of observations from dozens or hundreds of cosmic visitors will eventually allow comprehensive statistical analysis of conditions throughout our galactic neighborhood. The diversity of interstellar objects likely reflects the tremendous variety of planetary systems throughout the Milky Way galaxy. Some visitors may come from systems dominated by gas giants, others from regions rich in rocky worlds, and still others from environments unlike anything in our solar system. Each messenger carries unique information about its place of origin. Advanced propulsion concepts currently under development may eventually enable robotic missions to intercept and study interstellar objects during their passage through our solar system. Such missions could return physical samples to Earth for detailed laboratory analysis, providing unprecedented insights into alien materials and chemistry. The detection of biosignatures, or complex organic molecules in interstellar objects, would represent one of the most profound discoveries in human history, potentially providing evidence that life exists elsewhere in the galaxy. Even simple organic compounds would demonstrate that the chemical precursors for life are widespread throughout cosmic environments. International cooperation in interstellar object research is establishing frameworks for sharing data and coordinating observations that will benefit future discoveries. These collaborative networks ensure that humanity's response to cosmic visitors maximizes scientific return while engaging diverse global perspectives in the research process. Educational initiatives inspired by interstellar objects are cultivating new generations of scientists and engineers who will develop even more advanced techniques for studying these cosmic messengers. Student involvement in real research projects provides authentic experiences that inspire continued engagement with space science and exploration. 3I Atlas and its successors represent harbingers of humanity's expanding cosmic perspective, reminding us that our solar system exists within a dynamic galactic environment where material and information flow freely between star systems. These cosmic visitors connect us directly to the broader universe and our shared cosmic heritage. The future promises even more remarkable discoveries as our detection capabilities improve and interstellar visitors become routine subjects of scientific investigation rather than rare, unexpected events. The journey of 3I Atlas through our solar system tells a profound story that extends far beyond a single cosmic visitor. This remarkable object, racing through space at record-breaking velocities with the most extreme trajectory ever recorded, represents our first glimpse into a new era of interstellar science, where the universe delivers its secrets directly to our cosmic doorstep. From its near miss with detection while hidden against the crowded star fields of the galactic center, to the collaborative efforts of citizen scientists who extended its discovery timeline, 3I Atlas demonstrates both the challenges and opportunities that define 21st century astronomy. The global race to study this visitor before it disappears forever showcases humanity at its scientific best, working together to unlock cosmic mysteries. What makes this discovery truly revolutionary is not just what we have learned, but what it promises for the future. The Vera C, Rubin Observatory and next-generation survey systems will soon transform rare interstellar visitors into routine scientific opportunities, providing regular access to material and information from distant worlds throughout our galactic neighborhood. 3I Atlas carries within its ancient nucleus and developing coma the chemical signatures of another star system, offering direct samples of alien world-building materials that we could never hope to reach through conventional space travel. Each spectroscopic measurement and photometric observation adds crucial data to our understanding of how planetary systems form and evolve throughout the galaxy. As this cosmic messenger completes its brief visit to our solar system and races back into the depths of interstellar space, it leaves behind a transformed astronomical community equipped with new capabilities, deeper understanding, and elevated expectations for future discoveries. The age of interstellar object science has truly begun. The chase may be ending for 3I Atlas, but the greater journey of cosmic exploration continues, guided by the knowledge that we live in a galaxy filled with wandering worlds waiting to tell their stories to anyone prepared to listen.